1940. War Department Headquarters, Washington, D.C. European automotive engineers reviewing American military vehicle specifications would dismiss what they read as mechanically impossible. A vehicle weighing under 1,300 pounds, carrying 600 pounds of cargo, seating 3 soldiers, fording 29 centimeters of water, reaching 50 miles per hour, all for under $750 per unit. Through the corridors of American engineering firms, blueprints scattered across drafting tables told a different story than European tradition demanded. No precision machining, no exotic materials, no sophisticated timing mechanisms, just cast iron simplicity that could be rebuilt with basic hand tools in a muddy foxhole. European engineers had spent decades perfecting complex automotive systems that required master technicians and specialized equipment for every repair. Their vehicles were marvels of engineering sophistication, multiple overhead cams, intricate gear systems, precision-manufactured components that delivered impressive performance under ideal conditions. The Americans were designing with a completely opposite philosophy: simplicity over sophistication, field repair over factory precision, soldier maintenance over specialist knowledge. 85 years later, those impossible American vehicles still climb mountains while modern luxury SUVs break down from software updates. The morning of July 11, 1940, Colonel Arthur W.S. Harrington spread the War Department's latest procurement specifications across his mahogany desk and wondered if someone in Washington had lost their mind. The single-page document demanded a light reconnaissance vehicle, weighing no more than 1,300 pounds, capable of carrying 600 pounds of equipment plus 3 fully armed soldiers, equipped with 4-wheel drive, able to ford water 29 centimeters deep, and capable of reaching 50 miles per hour on roads. The final requirement made his jaw clench. Unit cost not to exceed $750. Harrington had spent the previous month reviewing submissions from European automotive consultants, each filled with detailed explanations of why American industry lacked the precision manufacturing capabilities for modern military vehicles. Mercedes-Benz engineers had submitted a 47-page technical analysis demonstrating that proper military transport required sophisticated valve timing, precision machined gear systems, and specialized metallurgy that only German factories could provide. British automotive specialists concurred, noting that reliable 4-wheel drive systems demanded complex transfer cases and differential mechanisms beyond American manufacturing tolerances. The colonel pushed back from his desk and walked to the window overlooking the Potomac. European automotive engineering had dominated military procurement for 2 decades, and with good reason. Their vehicles featured advanced overhead valve engines, intricate transmission systems, and precision-manufactured components that delivered consistent performance under demanding conditions. When the British Army needed reliable transport, they contracted with Rolls-Royce. When French forces required reconnaissance vehicles, they turned to Peugeot's sophisticated engineering teams. American automobile manufacturers built reliable civilian cars, but military specifications demanded engineering precision that Detroit had never demonstrated. Yet the specifications sitting on his desk represented something more desperate than peacetime procurement. Intelligence reports from Europe painted an increasingly grim picture. German forces were advancing through France with mechanized efficiency that made traditional cavalry and infantry tactics obsolete. American military planners faced an uncomfortable reality. The United States might soon find itself fighting a mechanized war across multiple continents, requiring hundreds of thousands of vehicles that could be produced quickly, maintained easily, and operated by soldiers with minimal mechanical training. The procurement timeline made European precision manufacturing impossible. The War Department had allocated 49 days for American manufacturers to submit working prototypes. European automotive firms typically required 6 months just to finalize engineering specifications, followed by another year of testing and refinement before production could begin. Mercedes-Benz had politely declined to participate, explaining that proper military vehicle development required a minimum of 18 months from initial design to production-ready prototypes. Harrington returned to his desk and examined the 3 American responses that had arrived that morning. Bantam Car Company, a struggling manufacturer from Butler, Pennsylvania, submitted a brief proposal featuring hand-drawn sketches and estimated specifications. Their chief engineer, Karl Probst, claimed he could deliver a working prototype within the 49-day deadline using existing automotive components and simplified engineering approaches. Ford Motor Company's response was more conservative, requesting additional time to develop proper testing protocols and quality assurance procedures. Willys Overland Motors submitted the most ambitious proposal, promising not only a working prototype, but also detailed production plans for manufacturing 50,000 units within the first year. The Willys submission caught Harrington's attention because of its engineering philosophy rather than its technical specifications. Their chief engineer, Delmar Roos, had included a single-page explanation of what he called battlefield maintenance design. Instead of pursuing European-style precision manufacturing, Willys proposed building vehicles with components that could be repaired or replaced using basic hand tools and readily available materials. Their proposed engine was a simple flathead four-cylinder design with no overhead valves, no complex timing chains, and no precision machine components that required specialized replacement parts. European consultants would consider such simplification primitive, but Harrington recognized the operational logic. American forces fighting in North Africa or the Pacific would face supply line challenges that made European-style precision maintenance impossible. A reconnaissance vehicle that broke down 200 miles from the nearest depot needed to be repairable by soldiers using battlefield improvisation, not specialist technicians with factory-calibrated equipment. The more Harrington studied the American proposals, the more he realized they represented a fundamentally different approach to military engineering. European manufacturers designed vehicles to meet ideal performance specifications under controlled conditions. American manufacturers were designing vehicles to function under the worst possible conditions with minimal support infrastructure. European vehicles were engineering marvels. American vehicles were engineering tools. The contrast crystallized when he compared engine specifications. The proposed German military engine featured dual overhead cams, precision-timed valve systems, and metallurgy that required specialized manufacturing equipment. The Willys Go Devil engine used a simple flathead design with side valves, cast iron construction, and tolerances loose enough that replacement parts could be manufactured in field workshops. German engineering delivered superior horsepower and fuel efficiency. American engineering delivered reliability and repairability. By late afternoon, Harrington had reached a decision that would have seemed impossible that morning. The European consultants were probably correct about American manufacturing lacking sophistication, but they were asking the wrong question. The issue wasn't whether American industry could build vehicles as precisely engineered as European models. The question was whether American industry could build vehicles that American soldiers could keep running under combat conditions, where precision engineering became a liability rather than an asset. He picked up his telephone and placed the first call to Butler, Pennsylvania. In 49 days, he would discover whether American common sense could outperform European sophistication, or whether he was about to equip American soldiers with vehicles that would get them killed. By October 15, 1941, the assembly line at Willys Overland's Toledo plant was producing 150 vehicles per day, but Delmar Roos knew the numbers weren't sustainable. Standing on the factory floor at 5:30 in the morning, watching the third shift struggle to maintain production quotas, he calculated the grim mathematics of military procurement. The War Department had increased their initial order from 1,600 units to 25,000, with delivery deadlines that made European manufacturing timelines look leisurely. His workers were pulling 12-hour shifts 6 days a week, and the bottlenecks were becoming critical. The problem wasn't worker dedication or factory capacity. The issue was component complexity cascading through every stage of production. Each vehicle required 847 individual parts, from major assemblies like the transmission housing down to specialized bolts and gaskets. European manufacturing philosophy dictated that each component meet precise specifications with minimal tolerances, ensuring perfect fit and optimal performance. But precision manufacturing created production choke points that made mass production impossible under wartime deadlines. Roos had spent the previous month redesigning the vehicle from the ground up, not to improve performance but to simplify manufacturing. The original prototype featured a complex four-wheel drive system with multiple gear ratios and sophisticated differential mechanisms. His production model used a simplified transfer case with fewer moving parts and looser manufacturing tolerances. The steering system eliminated precision-machined components in favor of robust cast-iron assemblies that could be produced quickly and replaced easily. Every design decision prioritized manufacturing speed over engineering elegance. The breakthrough came when Henry Ford's procurement team arrived in Toledo with an unexpected proposal. Ford Motor Company had analyzed the military specifications and concluded that no single manufacturer could meet the production volumes the War Department required. Instead of competing for the contract, Ford offered to produce vehicles identical to the Willys design, ensuring complete interchangeability of components between manufacturers. Two factories would build the same vehicle using identical specifications, doubling production capacity while maintaining engineering consistency. The Ford proposal violated every principle of automotive competition, but Rouse recognized its operational genius. Interchangeable parts meant that a transmission from the Toledo plant could be installed in a vehicle assembled in Dearborn, Michigan. A soldier in North Africa could cannibalize components from two damaged vehicles to create one functional unit. Supply chains could be simplified because every replacement part worked in every vehicle, regardless of manufacturing location. Implementation required unprecedented cooperation between competing manufacturers. Ford engineers spent 3 weeks in Toledo studying Willys' production methods, documenting every manufacturing process and quality control procedure. Willys engineers traveled to Dearborn to ensure Ford's assembly line could replicate their specifications exactly. The two companies shared proprietary manufacturing techniques, supplier relationships, and quality assurance protocols that would normally be closely guarded trade secrets. The engineering specifications that emerged from this collaboration reflected pure American pragmatism. The chassis used a simple ladder frame construction with straight rails and cross members that could be welded by semi-skilled workers using basic equipment. The suspension system employed leaf springs front and rear, eliminating the complex coil spring assemblies that European manufacturers preferred. The body panels were designed with generous tolerances and minimal compound curves, allowing them to be stamped using existing automotive tooling rather than specialized military manufacturing equipment. Most significantly, the engine compartment was designed for accessibility rather than aesthetics. European military vehicles typically housed their engines in tightly packaged compartments that maximized space efficiency but made field maintenance nearly impossible. The Willys design provided generous clearance around every major component, ensuring that soldiers could remove and replace parts using standard hand tools. The battery, oil filter, spark plugs, and distributor were positioned for easy access without removing other components. By February 19, 1942, both factories were producing vehicles at rates that impressed even skeptical military observers. The Toledo plant delivered 230 units per day, while Ford's Dearborn facility produced 180 identical vehicles using the same specifications. Quality control inspectors found that parts manufactured in Michigan fit perfectly in vehicles assembled in Ohio, validating the interchangeability concept under actual production conditions. The real test came when the first production vehicles reached military training facilities. Soldiers with minimal automotive experience were able to perform routine maintenance using basic tools and standard procedures. Oil changes required 15 minutes and a single wrench. Spark plug replacement took 20 minutes without removing any other components. Transmission service could be completed in field conditions using equipment carried in the vehicle's standard toolkit. Colonel Harrington received his first operational report from Fort Benning in March. Training instructors noted that recruits who had never worked on automobiles could master basic maintenance procedures within 1 week of instruction. More importantly, the vehicles continued functioning despite maintenance mistakes that would have disabled more sophisticated European designs. Loose oil drain plugs, improperly gapped spark plugs, and incorrect fluid levels caused performance degradation but rarely resulted in complete mechanical failure. The production statistics told the story of American industrial capability unleashed. By June 20th, 1942, the two factories had produced 28,000 vehicles with identical specifications and complete parts interchangeability. European Automotive, consultants who had dismissed American manufacturing capabilities as inadequate for military requirements, were studying reports of production rates that exceeded their most optimistic projections. But the ultimate validation would come not from factory efficiency or maintenance simplicity. The real test would be whether vehicles designed for American practicality could survive the brutal conditions of mechanized warfare across multiple continents, where engineering theory would meet the unforgiving reality of combat. Technical Sergeant Michael Kowalski crouched beside his disabled Willys in the Tunisian desert, 23 miles southeast of Kasserine Pass, and discovered what American engineering philosophy meant under combat conditions. The vehicle had taken shrapnel from a German 88mm shell that punctured the radiator, severed two spark plug wires, and cracked the oil pan. Any European military vehicle would require depot-level maintenance and specialized replacement parts. Kowalski had the Willys running again in 47 minutes, using battlefield improvisation and the standard toolkit. The radiator repair involved hammering the punctured section flat and sealing it with soap from his shaving kit mixed with sand. European cooling systems used precision-manufactured components with tight tolerances that made field repairs nearly impossible. The Willys radiator was built with generous clearances and robust construction that could function with reduced cooling capacity. Kowalski rerouted the damaged spark plug wires using electrical tape and wire from a destroyed German radio, while the cracked oil pan was sealed with a combination of engine gasket material and metal from a discarded ration can. Within 2 hours, Kowalski's improvised repairs were being replicated across the North African theater. The simplicity of American engineering design meant that soldiers with basic mechanical knowledge could maintain their vehicles using materials scavenged from the battlefield. German forces, accustomed to precision-manufactured military equipment that required specialized maintenance facilities, were baffled by American vehicles that continued functioning despite obvious damage and crude field repairs. Italian intelligence reports from the Tunisian campaign described American reconnaissance units as pattuglia fantasma because of their ability to appear in unexpected locations despite apparent mechanical damage to their vehicles. What Italian observers interpreted as supernatural resilience was actually the practical result of engineering designed for soldier maintenance rather than factory precision. American vehicles could be repaired by 19-year-old farm boys using improvised tools, while Axis military equipment required trained technicians with specialized replacement parts. The operational advantages became clear during the Sicily campaign when American forces discovered that their simplified maintenance requirements created unexpected tactical flexibility. While German mechanized units were constrained by supply lines that delivered precision-manufactured replacement parts, American forces could maintain their vehicles using components cannibalized from damaged units or improvised from available materials. A single destroyed Willys could provide functional parts for 3 or 4 damaged vehicles, effectively multiplying the operational lifespan of American equipment. Captain James Morrison of the 3rd Armored Division documented the phenomenon in his after-action report from the Anzio beachhead. His reconnaissance platoon had operated for 18 days behind German lines using 4 Willys vehicles that had been mechanically written off by European standards. 2 had cracked engine blocks sealed with improvised gaskets. 1 was running on 3 cylinders with a destroyed piston, and the 4th had a transmission that had lost second gear entirely. All 4 vehicles continued functioning throughout the mission, providing critical intelligence that influenced the successful breakout from the Anzio perimeter. The engineering philosophy that Delmar Roos had implemented in Toledo was proving itself under conditions that no European automotive engineer had anticipated. Loose manufacturing tolerances meant that American vehicles could function with damaged or worn components that would immobilize more precisely engineered equipment. Simple mechanical systems could be repaired or bypassed using basic tools and soldier ingenuity. Robust construction allowed vehicles to continue operating despite damage that would require depot-level repairs for European military equipment. By November 1943, American forces had deployed 47,000 Willys vehicles across 3 continents from the Aleutian Islands to North Africa to the Pacific Theater. Soviet forces operating under Lend-Lease agreements reported that American vehicles required 60% less maintenance time than comparable British or German equipment. Red Army mechanics noted that the Willys could be serviced using tools and techniques already familiar to soldiers who had maintained Soviet agricultural equipment, while British military vehicles required specialized training and precision-manufactured replacement parts. The most dramatic validation came during the Battle of the Bulge, when German forces captured intact American supply depots, containing hundreds of Willys vehicles. German mechanics attempted to service the captured equipment using their standard precision maintenance procedures, only to discover that American engineering tolerances were so generous that German precision tools were unnecessary. Components that German engineers would have rejected as inadequately manufactured continued functioning reliably under combat conditions. Wehrmacht technical reports described American military vehicles as crudely constructed but mechanically sound, reflecting European bias toward precision manufacturing that missed the operational advantages of American simplicity. German forces discovered that captured Willys vehicles could be maintained using improvised tools and salvaged materials, but their own military equipment required specialized maintenance facilities that were increasingly unavailable as Allied bombing disrupted German supply lines. The statistical evidence was overwhelming by spring 1944. American forces reported mechanical availability rates of 87% across all theaters compared to 63% for British forces using precision-manufactured military vehicles. Soviet units equipped with American vehicles under Lend-Lease demonstrated operational readiness rates that exceeded their own domestically manufactured equipment by 32%. The simple engineering philosophy that European consultants had dismissed as inadequate was proving superior under actual combat conditions. Most significantly, the battlefield performance validated the original design philosophy that had emerged from those 49 days in 1940. Vehicles designed to be repaired by soldiers using basic tools were outperforming equipment designed by Europe's most sophisticated automotive engineers. American common-sense engineering was defeating European theoretical precision under the ultimate test of mechanized warfare, proving that simplicity and reliability trumped complexity and sophistication when lives depended on mechanical performance. Dr. Elena Martinez stared at the diagnostic readout from her latest SUV prototype and wondered how automotive engineering had become so complicated that a simple sensor failure could disable an entire vehicle. The luxury SUV sitting in her Michigan testing facility contained 151 electronic control units managing everything from engine timing to seat position memory, connected by over 4 miles of wiring harness, and communicating through 37 different network protocols. A single corrupted software module in the body control unit had triggered cascade failures that left the $85,000 vehicle completely inoperable, despite having a perfectly functional engine and transmission. The contrast with the 1943 Willys Jeep parked in the adjacent bay was impossible to ignore. That vehicle contained 0 electronic control units, 12 feet of basic wiring for lights and ignition, and mechanical systems that could be diagnosed by listening to engine sounds and observing visible components. Martinez had watched the facility's senior technician, a 62-year-old mechanic named Frank Kowalski, grandson of the World War II sergeant, diagnose and repair the Willys using hand tools and 30 minutes of troubleshooting that relied entirely on mechanical knowledge rather than computer diagnostics. Modern automotive engineering had evolved into a discipline that prioritized technological sophistication over mechanical reliability. The SUV prototype featured adaptive air suspension with 15 sensors monitoring ride height, damping rates, and road conditions, automatically adjusting suspension characteristics 50 times per second. The system delivered superior ride quality and handling compared to simple leaf springs, but a single sensor failure rendered the entire suspension inoperable, leaving the vehicle stranded until specialized diagnostic equipment could identify the malfunctioning component and dealer-only replacement parts could be installed. The engineering complexity extended throughout every system. The engine management computer processed input from 43 sensors, monitoring everything from exhaust gas composition to ambient air temperature, making fuel delivery and ignition timing adjustments thousands of times per minute. This sophisticated control delivered exceptional fuel efficiency, and emissions compliance that would have been impossible with the simple carburetor and mechanical ignition system of the Willys. But the electronic complexity meant that engine problems required specialized diagnostic equipment and software updates rather than the basic mechanical troubleshooting that had kept Willys Jeeps running for 80 years. Martinez had begun her career believing that engineering progress meant adding capability and sophistication to automotive systems. Her MIT education emphasized optimization algorithms, integrated system architecture, and electronic control strategies that could deliver performance impossible through purely mechanical means. The air suspension system she had designed could automatically adjust ride height for aerodynamic efficiency at highway speeds, lower the vehicle for easier entry and exit, and provide ground clearance adjustment for off-road conditions. No mechanical system could duplicate this functionality. The financial implications of this complexity were staggering. Martinez's cost analysis revealed that the average luxury SUV owner spent $5,700 annually on maintenance and repairs, with electronic system failures accounting for 68% of service visits. A typical air suspension repair cost between $2,400 and $4,100, requiring specialized diagnostic equipment that only authorized dealers possessed. The integrated nature of modern vehicle systems meant that seemingly minor component failures often triggered expensive repairs involving multiple systems. The reliability statistics were equally troubling. Modern vehicles averaged 1.2 mechanical failures per year requiring professional service, compared to the 0.3 failures per year that mechanics reported for properly maintained vehicles from the 1970s and 80s. The increased failure rate wasn't due to inferior manufacturing quality, but rather the exponential increase in system complexity. Each additional electronic control unit represented another potential failure point, while the integrated nature of modern systems meant that single component failures could cascade through multiple vehicle systems. The contrast became painfully obvious during Martinez's company's off-road testing program. Their flagship SUV, equipped with advanced terrain management systems, electronic traction control, and sophisticated all-wheel drive algorithms, became completely disabled when a rock impact damaged the vehicle's computer network wiring harness. The physical drivetrain remained undamaged and fully functional, but electronic system failures prevented the engine from starting and the transmission from engaging. The same rock impact on the 1943 Willys might have dented the body panels, but would not have affected the vehicle's basic operational capability. Recovery from the trail required a specialized flatbed truck equipped with diagnostic equipment and a technician trained in the vehicle's electronic systems. The repair process involved replacing the damaged wiring harness, reflashing multiple computer modules with updated software, and recalibrating sensor systems using dealer-exclusive diagnostic protocols. Total repair time exceeded 40 hours and cost over $6,800. The comparable repair on the Willys would have involved bypassing damaged wires using basic electrical techniques that any mechanically competent individual could perform with hand tools. The engineering paradox extended beyond individual vehicle reliability to broader questions of automotive sustainability. Modern SUVs were designed with planned obsolescence cycles of 10 to 12 years, after which the cost of electronic system repairs exceeded vehicle value and forced replacement. The sophisticated diagnostic equipment required for maintenance became obsolete as manufacturers updated communication protocols and software architectures. Independent mechanics couldn't afford the constant equipment updates required to service modern vehicles, creating monopolistic dependence on dealer service networks. Meanwhile, thousands of Willys Jeeps continued operating after 80 years of service, maintained by owners using basic mechanical knowledge and readily available tools. The simple engineering that European consultants had dismissed as primitive in 1940 had proven more durable and sustainable than the sophisticated systems that contemporary automotive engineers considered advanced. Martinez was beginning to suspect that engineering progress had somehow become engineering regression disguised as technological advancement. The revelation came to Dr. Martinez during a July morning in 2024, when she discovered that the most reliable modern SUVs succeeded by deliberately avoiding the complexity that had defined contemporary automotive engineering. Toyota's 4Runner, consistently rated among the most dependable vehicles in its class, used a naturally aspirated V6 engine with port fuel injection rather than the sophisticated direct injection and turbocharging systems that other manufacturers had adopted. The transmission was a conventional 6-speed automatic without the complex continuously variable transmission technology or 10-speed units that promised improved efficiency but delivered increased failure rates. Honda's approach with the CR-V followed similar engineering philosophy, eschewing advanced all-wheel drive systems with electronic torque vectoring in favor of a simple real-time AWD system that used mechanical components and basic electronic controls. The vehicle featured traditional McPherson strut suspension rather than adaptive damping systems, manual climate controls alongside the electronic systems, and engine management that prioritized reliability over maximum performance optimization. These design choices resulted in significantly lower repair costs and higher long-term reliability ratings compared to more technologically advanced competitors. The statistical evidence was overwhelming when Martinez compiled reliability data across the automotive industry. Vehicles with naturally aspirated engines averaged 43% fewer powertrain-related failures than turbocharged equivalents. Traditional automatic transmissions required major repairs 68% less frequently than continuously variable transmissions or complex multi-speed units with electronic shift algorithms. Mechanical all-wheel drive systems demonstrated failure rates 72% lower than electronically controlled torque vectoring systems that promised superior performance but delivered expensive maintenance requirements. The pattern extended beyond individual components to entire vehicle architectures. The most reliable SUVs featured separate body-on-frame construction, similar to the original Willys design, rather than unibody architectures that integrated structural and aesthetic elements into complex assemblies. Body-on-frame vehicles could sustain significant damage to body panels or frame components without affecting other systems, while unibody designs often required extensive repairs when single elements were damaged. The engineering simplicity that had made battlefield repairs possible in 1943 continued delivering practical advantages 80 years later. Martinez began tracking the operational history of vehicles that had survived beyond typical ownership cycles, discovering that mechanical simplicity determined long-term viability. A 1998 Toyota 4Runner with over 400,000 miles remained fully functional using original powertrain components and basic maintenance procedures. The owner, a Montana rancher named Bill Henderson, performed all routine service using hand tools and readily available parts, spending an average of $600 annually on maintenance that kept the vehicle operationally reliable. The same rancher had previously owned a 2015 luxury SUV with advanced electronic systems that became economically unviable after 7 years when electronic component failures exceeded the vehicle's remaining value. The sophisticated terrain management system failed at 89,000 miles, requiring $4,200 in repairs involving dealer-exclusive diagnostic equipment and proprietary replacement parts. The air suspension system developed leaks that cost $3,800 to repair, while the infotainment system required software updates that eventually became incompatible with the vehicle's aging electronic architecture. The contrast illuminated the fundamental engineering philosophy that Karl Probst and Delmar Roos had established during those crucial 49 days in 1940. They had designed vehicles to be maintained by users with basic mechanical knowledge rather than specialized technicians with proprietary equipment. Modern automotive engineers had reversed this philosophy, creating vehicles that required manufacturer-controlled service networks and planned obsolescence cycles that forced replacement rather than repair. The global perspective reinforced these conclusions when Martinez studied international automotive markets. In regions with limited dealer networks and lower average incomes, the most successful vehicles featured mechanical simplicity and user-serviceable components. The Toyota Land Cruiser, legendary for reliability in remote locations, used naturally aspirated engines, mechanical fuel injection, and robust manual transmissions that could be serviced using basic tools and widely available parts. These vehicles routinely operated for decades with minimal professional service, maintained by owners who understood basic mechanical principles. The engineering lessons from World War II remained relevant because the fundamental challenges hadn't changed. Remote locations still demanded vehicles that could be repaired without specialized equipment. Budget constraints still favored simple systems over sophisticated alternatives. User competence still varied widely, making complex systems inappropriate for general use. The Willys Jeep had succeeded because it addressed these universal challenges through engineering design rather than technological complexity. Martinez realized that the most significant engineering advancement would involve returning to first principles rather than adding additional sophistication. Modern manufacturing techniques could produce simple mechanical systems with reliability that exceeded both historical standards and contemporary complex alternatives. Computer-aided design could optimize basic mechanical components for durability and serviceability. Advanced materials could improve the strength and longevity of simple systems without adding complexity that compromised field repairability. The vindication was complete when Martinez discovered that over 47,000 original Willys Jeeps remained operational worldwide in 2024. Many had exceeded 1 million miles of service through multiple rebuilds using basic tools and widely available components. Their simple engineering had proven more sustainable than sophisticated systems designed with planned obsolescence. The vehicles that European engineers had dismissed as mechanically primitive had demonstrated superior longevity, lower operating costs, and greater practical utility than contemporary alternatives designed using advanced engineering principles. American engineering genius had never been about building the most complex systems possible. It was about solving problems with the simplest effective solutions, creating tools that worked when sophisticated alternatives failed. The 19-year-old soldiers who had maintained Willys Jeeps in muddy foxholes had more in common with contemporary users than automotive engineers had recognized. The question that had guided every design decision in 1940 remained the most important engineering criterion in 2024. Can ordinary people keep this working when everything else fails?